Okay, good afternoon, everyone. My name is Ruijie Zhu. Today, I'm excited to present my work on diffusion modeling, high-throughput screening, and molecular dynamics for rational discovery of novel metal-organic frameworks for carbon capture at scale. Before I start, I would like to acknowledge the PIs and students that I worked with over the past year. Without them, I wouldn't be able to present my work today. Today, I would like to introduce a type of material called metal-organic framework. So the first question is, what is metal-organic framework? Essentially, this is a type of nanocrystalline material with three major components. The metal node, which is essentially a inorganic cluster with multiple connection points. And we also have the organic linker, which are molecules with two connection points. And the topology, which defines how the metal nodes are connected to the organic linkers. MOFs have been used in many applications. For example, they can be used for gas storage and separation. They can be used as for catalysis, and as well as drug discovery. In our work, we focus on the first application, and specifically, we design a new computational framework to accelerate the discovery of MOFs with high CO2 capacity. The database that we worked with is called the HMOF database. Here, H means hypothetical. Essentially, it is a type of computational database with more than 137K MOF structures, along with gas absorption isotherms. And if you look at the database, you'll find that there are three most frequent node topology pairs: the copper pedal PCU, the zinc pedal PCU, and zinc tetramer PCU. Those three node topology pairs constitute more than 70% of the entire database. And if you look at the pair plot of the MOF CO2 capacities at different pressures, you'll find that at different pairs of pressures, the MOF CO2 capacities are weakly correlated, which means that it is highly pressure dependent. And on the diagonal line, here we show the distribution of MOF CO2 capacities at the specific pressure. So what you find is that across the board, there are more MOFs with lower CO2 capacity, whereas there are only very few of them with high CO2 capacity. This motivates us to design new computational framework to accelerate the discovery of high-performing MOFs. The other concept I would like to introduce is called MOF catenation. So in the HMOF dataset, there are 4 catenation levels. It ranges from Cat0 all the way to Cat3. For Cat0, it is essentially a primitive lattice with no interpenetration. For Cat1, there are 2 interpenetrated lattices, and so on. So as you introduce more interpenetration of lattices, the pore size of MOFs becomes smaller. And so, which means that catenation can be a good way to tune the pore size of those MOFs, and therefore the gas absorption properties. So here's how our framework works. The first component of our framework is what's so-called decompose. So we start from the HMOF dataset, and we pre-select a type of node topology pair. So in this case, we're selecting the zinc tetramer PCU node topology pair. And we want to find the high-performing structures with this given node topology pair. So here, high-performing is defined as MOFs with CO2 capacity larger than 2 millimole per gram. And once we have those high-performing structures, we can use a tool called MOFID to parse the building blocks of those MOFs. Since we have fixed the node and topology, we can vary. We want to find new linkers that yield high-performing MOF structures. So our goal is to design new linkers. So in our case, we use MOFID to find those unique linkers in those high-performing MOF structures. We then applied a algorithm called MMPA to fragment those MOF linkers into their corresponding linker fragments. So now we have the fragments. What do we do next? We can use a type of diffusion model called difflinker that was proposed last year to sample new MOF linkers. So essentially, we start from the input fragments, and then we want to identify how many atoms we want to sample in between those fragments. And then we use a generative denoising process to diffuse those atoms into the desired positions. So we get their spatial coordinates as well as the elements of those atoms. And since it is a probabilistic model, we may end up with different configurations of those linker molecules. So this is exactly what we did. We start from the linker fragments, and we use the diff linker model to sample the number of atoms that we want, and as well as the atomic positions that we want. So, however, the output of those diff linker models were the heavy atom linkers, and so we need to add back the hydrogen atoms to make them four atom linker molecules. However, there's another step that we need to do. That is, we need to identify the dummy atoms, which are the atoms that specify, how those molecules are connected to the metal nodes. So once we do that, we can screen those molecules, remove those linkers with, unwanted elements, and we can use different metrics to evaluate the quality of those molecules. So we end up with a pool of candidates of those linker molecules. The final step is to assemble them with the pre-selected metal nodes and the topology, and so we end up with new MOF structures. So once we have all the generated structures, we can then use a regression model to predict their CO2 capacity. So in our case, we use the modified version of CGCN model that was developed in our previous work to make predictions of the CO2 capacities of those MOF structures. So here I'm showing the prediction results on the 10% tech set of the HMOF database. Here we can see that most of the points lie along the diagonal line, and there are very few of them that are further away from the diagonal line, which means that our model does a great job predicting the high and low performing structures. And here I'm showing the components as well as the predicted CO2 capacities of top 5 candidates generated using our framework. As you can see that all 5 are catenated MOFs. And the highest performing one that we found has a CO2 capacity of 2.51 millimole per gram at 0.1 bar. We also, and here is the 3D visualization of the top 5 candidates. We also used a molecular dynamics simulation to examine the stability of those top 5 candidates. And what we found is that all 5 of them have negligible density change during the MD simulation, which verifies their stability. So, in conclusion, we propose a computational framework to accelerate the rational design of MOF structures with high CO2 capacity. Out of the 120K candidates, we found that 18 structures possess both high CO2 capacity at 0.1 bar and negligible structural change during the MD simulation.